Good afternoon, everyone. I hope you had a good weekend. For those of you who are wondering, I did pass my PhD defense, so I guess that makes me Dr. Professor Amber now. Hopefully you're old enough to appreciate SpongeBob references, but in seriousness, you can still just call me Amber. I'm just having a little fun with the title for now, but Amber is fine. So we have a lot of material we're going to get through today, but the hope is that we'll have a lighter day on Wednesday, so you'll have time to ask any questions, potentially do a little bit of review. So we're going to start with thin film interference. And so let's suppose we have a puddle and there's a little thin layer of oil on the surface of the puddle. And we're going to zoom in on it really close. So that layer of oil is really, really thin, but we're going to zoom in on it so we can actually see it. And so this is our oil layer right here. And it's sitting on top of water. And we have air up here. Now we're going to have a ray of light and it's going to come through our air into our oil and then down into our water. So this is the light ray. Now some of the light ray is going to transmit all the way through, but some of it's going to reflect at the different boundaries. So you could have some light that hits the air-oil boundary and bounces, and you could have some that hits the oil-water boundary and bounces. So we're going to draw, all this is happening along this line, but just so we can actually see the different lines, we're going to draw them off to the side. And so we'd have one here, that's the one that's reflecting at the air-oil boundary. And we have another one over here that's reflecting at the oil-water boundary. Now for air, the index of refraction is about 1. Oil, it varies. For this particular oil, we're going to say it's about 1.2. And water has an index of refraction of about 1.33. And that will be relevant in a moment. So we have these two light rays, and they can interfere constructively or destructively because they're both being reflected and they're being reflected in the same space. So again, everything that's happening is happening right along this line. We just move them over so you can see where they're at, because otherwise they would just overlap over each other. So I know Mr. Douche has given us a little sheet basically on Blackboard that shows the steps of figuring out the interference for thin films. And so our first step is to identify whether our rays that are coming through are going to be inverted or uninverted. So if we have, if we're going from a low index of refraction to a high index of refraction, we're going to be inverted. If we go from high to low, we're going to be uninverted. So inverted is low to high. Uninverted is high to low. So we're going to look at each of these two situations, so when we're going from air to oil and then from oil to water, and see whether we're inverted or uninverted. So when we're going from air to oil, well, this index of refraction is lower than this one, so we're going low to high. So air to oil is going to be inverted. And then when we go from oil to water, well, again, we're going from a lower index of refraction to a higher index of refraction. So we're going to be inverted here as well. So oil to water, that's also inverted. So step 1 is just determining whether they're inverted or uninverted. So we'll say step 1. Step 2, and that's going to be at each boundary. So you're going to have one ray at this boundary, one ray at this boundary, and we have to figure out what's happening when we hit those boundaries. Our next step is to determine whether our interference is constructive or destructive. And so if they come out doing the same thing, so if they're either both inverted or both uninverted, they will interfere constructively. But if one comes out inverted and the other one comes out uninverted, then they're going to be interfering destructively. So step 2 is determining whether we have constructive or destructive interference. And for constructive, both inverted or both uninverted. And then for destructive, you have only one that's inverted. So the other has to be uninverted. That's our second step. Now step 3 is where things start getting a little bit tricky. Because what step 2 is telling us about is if these two rays were to come out at the same spot, would they be interfering constructively or destructively? The tricky thing, though, is they're not starting at the same location. This one's starting out up here. This one's starting out down here. It has to travel through this thin film, this thickness, some thickness here. So we have to consider how that's going to affect our wave. Is it going to shift it by a wavelength, by half a wavelength? So our next step is, once we know whether we have constructive or destructive interference, we're going to have to use one of our two equations, and we'll get to the equations in a second, to either keep things the same or shift them. So, and I don't think I said in this example here, but in our example we're doing, they both were uninverted, so they both are constructively interfering with each other. So in this specific case, we have constructive interference. Now, moving on to step 3, I think I'm going to need to erase our figure to have enough room for this. So step 3 is use the appropriate equation to keep or change our interference type. So a lot of times the question will tell us that it'll either say something like, maybe what it says that we have dark fringes, and then what would the thickness be, or we have bright fringes. It may not explicitly say we have constructive or destructive, so you may have to use your knowledge of constructive and destructive. We will tell you what type of interference you have, and you have to figure out how you get it. So if we want to keep the type of interference we have from step 2, then we're going to use our constructive equation. And we'll write out what the equation is in a moment. And this is kind of where a lot of people get stuck with thin film interference is the question will say, okay, we have these bright fringes, and then people will automatically be like, okay, it's constructive interference, let's go use the constructive interference equation. But if you had destructive interference in step 2, then you're going to be using the wrong equation. So if you have this, want to keep the same interference you found from step 2, then you want to use the constructive equation. If you want to change your interference, then you'll use the destructive equation. And the reason why this works is, so constructive interference happens at integer multiples of our wavelength. So if we take our wavelength and we shift it over, or take our wave and we shift it over by 1 wavelength, you're still going to have crests lining up with crests and troughs lining up with troughs. If instead we shift it over by half a wavelength, say, then you're going to be moving your crests to where there are troughs in the second wave, and your troughs to where there are crests in the second wave. So that's why the 2 different types of equations that you use will determine whether your interference is going to stay the same or flip. So let's write out what our equations are. And we'll start with constructive. And the condition is going to look very similar. So I'm going to use delta D to denote the path length difference like we have before. Now, what is our path length difference? Well, if we have our oil layer, and our light is coming down through, we have our first ray bounces at this boundary. Our second one, though, the one that goes down here, to get to this boundary, it has to come all the way down, so it goes all the way down to the oil once, and then it comes back up. So if this has some thickness to it, T, it has to travel that thickness twice before it hits this boundary and meets this wave. So delta D is going to be equal to 2T, and then from here the equation is going to look very similar. It's just going to be M, and we're going to use lambda material here because we're in a material, which is the same thing as M lambda vac over N. Now destructive is the exact same thing, except we're going to have the M plus 1/2 instead of M. So for destructive, we're going to have delta D is equal to 2T, because we're still traveling that twice the thickness. This is going to be M plus 1/2 lambda material, or M plus 1/2 lambda vac over N. Now, the question arises, what index of refraction are we using here? We're using the index of refraction of the material we're traveling through here, so this middle layer, our thin film. So in the case of our example we've been working with, this would be oil, so we'd use the 1.2. So the N we're using is just the one from that middle layer. You'll have an index of refraction up here and down here, but you only need to use the middle one in this equation. So are there any questions to this point? All right, so let's go to an example. Uh-oh, someone didn't rinse the dishes thoroughly. A thin film of soap, which has an index of refraction of 1.25, sits atop the water in Molly's bowl. So we have the index of refraction of our soap is 1.25, and the situation we're looking at is we have this layer of oil, or not oil, soaps, on top of the water in Molly's bowl, and so we have some, presumably, air above the bowl. You notice that constructive interference occurs for reflected light when you shine a green light, which has a lambda vacuum of 500 nanometers. So I'm going to use lambda sub GVAC to denote that it's the green light. And violet light. So we have constructive interference for two different situations. We shine a green light in, we got constructive interference. We're shining a violet light in, we're also getting constructive interference. So we'll have lambda VVAC equals 400 nanometers. Now if you're an astute observer, you will notice this is the wavelength I used for a red laser in last week's recitation. Just like I can't tell my left from my right, apparently I flipped the ends of the spectrum. So all this does is we were working with a violet laser the whole time last time, but the math is still the same. And now we corrected it so it's violet light that's 400 nanometers. So we want to know what is the smallest possible thickness of the soap layer. So that's what we're trying to figure out. We're told we have constructive interference. So we know constructive interference for these two wavelengths. So we have now, before we can pick an equation, we have to know what's happening with this. Are these going to be inverted or uninverted? And so let's find out our indices of refraction. So air, well, we know the wavelength there, or sorry, the index of refraction is about 1. We know the soap, we're told in the problem, is 1.25, and water is about 1.33. So before we can use any equation, we have to go through and see what's happening here. So going from air to soap, we're going to be inverted. Because this index of refraction is lower than this one. And similarly, going from soap to water, we're also going low to high, so we're also going to be inverted. Now, if both are inverted, that means we have constructive interference. So we have constructive interference here, and we have constructive interference at this end, so we want to keep it the same. Since we want it to stay the same, we're going to use the constructive interference equation. So if this had been destructive and destructive, we would still be using the constructive interference equation because we'd want to keep it the same. So even though it's called the constructive interference equation, you use it to keep things the same. So in this case, we have both constructive and constructive, so we're going to keep it the same. We're going to use constructive. So let's write out a statement of that equation, and then we'll look at what's tricky about the situation. So our constructive interference equation is that 2t is equal to m lambda vac over our index of refraction n. Now we know we have two different lambda values. We know the index of refraction of our soap. We don't know m for either of these. Now that's what makes things a little bit tricky. But what we can do is we're going to assign them an M value, not a numerical value, but we're going to say that the green light has a mode M equals M. So for green, we have M. Now we're looking for our thinnest film we can have, so if we just hop over by 1, when we go to violet, that's when it's going to occur. So violet is going to be M plus 1, because it's just one more. And so what we're going to do is we're going to write out the expression for green light and the expression for violet light. And we're going to use that to solve out for M. Once we have M, we can go ahead and plug that back into our equation and find the thickness of our soap layer. So we're going to have, if we write this out, we're going to have M lambda G vac over N equals M plus 1 lambda V vac over N. And we can say that these two things are the same because they have that, they're traveling that same thickness T. So they have to be the same expression. So this index of refraction here is the same for both because it's the index of refraction of the soap. So we can cancel that out. And we're going to have M lambda G vac equals M, and I'm going to expand this term. So M lambda V vac plus lambda V vac. I'm going to move the M terms over onto the same side and factor out the M. So we're going to have M times lambda G vac minus lambda V vac is equal to lambda V vac. We're going to divide both sides by this expression right here so we can get M by itself. So we're going to have M is equal to lambda V vac divided by lambda G vac minus lambda V vac. Now we're going to plug in our values. Now note that these two, the numerator and denominator, have the same units and the units are going to cancel. So in this particular instance, I'm going to leave it in nanometers, but I could have converted to meters. In this case, since the units cancel, it doesn't matter which one we use. So we're going to have VVAC, that's 400 nanometers, divided by 500 nanometers minus 400 nanometers. Well, this, if we have 500 over 100, that's going to leave us with M equals 4. So our final answer for this part, our M value, is M equals 4 for green light. So we can use either green light or violet light here. I'm going to go ahead and use the green light equation to find our thickness of our soap, but you could use the violet as well. You'll just have to add 1 to your M because that's M plus 1. So going back to our equation, thin film equation, we're going to have 2T equals M lambda G vac over N. Well, that's going to be 4. Now our lambda G vac, here I'm going to convert from nanometers to meters, so we're going to have 5.0 times 10 to the minus 7 meters, divided by our index of refraction is 1.25, and that works out to be about 1.6 times 10 to the minus 6 meters, and that's 2 times the thickness. So if we want T itself, we're just going to divide both sides by 2. So you're going to have T is equal to 1.6 times 10 to the minus 6 meters divided by 2, or 8.0 times 10 to the minus 7 meters. So are there any questions on this example? So for total internal reflection, we learned when we were doing lab last week that if we have light and we shine it into a medium, it can do one of two things. It can reflect or it can refract. Now last week in lab, we were allowed to pick our materials, but I think most of us used air, which has a very low index, well, practically 1 index of refraction, so very, very low, and then some medium that had a higher index of refraction. And so if you're shining something into something that has a higher index of refraction, then you can't get total internal reflection. But if you're going from a higher one to a lower one, you're going to find there's a certain place where you can't get your refraction happening anymore, only reflection. So I'm going to do a screen share real quick to show you when this happens. And so I'm just going to that simulator that we used last week. And so let's turn on our laser and let's turn on our angles as well. And let's change our medium. So I'm going to go with glass, which has a pretty high index of refraction. And we're going to go into water, which has a lower index of refraction. Now you'll notice that our water has a steeper angle than our glass. So as we push this further and further, we get to a point where this line has been getting weaker, but it just completely disappears when we hit an angle. So if you watch, it's hard to get it just right, but it's 90 degrees where that happens. So when this angle here hits 90 degrees, we no longer have any reflection, or any refraction, we just have reflection. So it can't even go into this material. The angle is too steep. So, if we think about what's happening there, so we have our two different mediums. We have our light coming in here, and we noticed that it was completely reflected. So let's draw our surface normal in. And it reflects when this angle reaches 90 degrees. So if this has some index of refraction N1, this has some index of refraction N2, this has some, oops, I drew the angle the wrong way, some angle theta 1 with respect to our surface normal. This has some angle theta 2, which is 90 degrees. So this right here, theta 2 equals 90 degrees. So if we were to use Snell's law on this, we're going to have N1 sine theta 1 equals N2 sine 90 degrees. Well, sine of 90 is just 1, so it's going to be N2. So if we solve out for our angle, we're going to find that we get total internal reflection when theta 1 is equal to the arc sine of N2 over N1. So when this ratio becomes too high, or when the angle exceeds this ratio, the arc sine of this ratio, then you're going to end up with not having any refraction anymore, only having total internal reflection. So let's suppose we have a glass prism, and we have some light coming into the bottom. And so this prism is glass and this outside is air. So our glass has an index of refraction of 1.5, and outside we're at air, so n is equal to 1.0. And I'm gonna draw on our surface normal. So we're gonna have some light that's coming in, and it's going to bend a little. So these angles are not the same. It kind of looks the same in my drawing, but they should be a little different. So this one's a steeper angle. And it's steep enough that this one is going to, when it hits this boundary, it can't come out into the air. It has to just bounce. And then when we get up here, then our angle is going to be shallow enough that it's able to come out and back into the air. And so our starting angle, which we'll call theta sub 1, theta 1 equals 30 degrees. We want to know what's our angle up here, and this one's going to end up being theta 6 when we go through and label them. So we want to know what is theta 6. So I'm going to call this angle theta 1. We'll call this one theta 2, theta 3, theta 4, and theta 5. So this may look really ugly and like it's going to be a nuisance to solve, but it turns out it's not so bad. All we have to do is a combination of Snell's law and some triangle geometry, which I guess is trigonometry. So we're going to use Snell's law at this boundary, and we're going to use Snell's law at this boundary. But in here, we're just using properties of right triangles and the fact that when something reflects, the angle of incidence is the same as the angle of reflection. So our first step is we need to use Snell's law. So we're going to have n1 sine theta 1 equals, I think we can get rid of our, no, it's good to have the figure there. So this is equal to n2 sine theta 2. So if we want to solve out for theta 2, we're going to have theta 2 is equal to the arc sine of, and now we're going to have n2 over n1 sine theta 1. So from here it's a matter of plugging in our values. So we're going to have theta 2 is equal to the arc sine of, now n2, that's going to, we're in the glass for that, so that's going to be, I just rearranged this upside down, it should be n1 over n2. So n1 we're in air for, so we're going to have 1.0 over 1.5, and then we're going to have sine of 30 degrees. Plug that into our calculator, and we're going to get that our angle is equal to about 19.47 degrees. So that's theta 2. Now to find theta 3, well, if we look at our normal lines, they're going to form a right triangle here. So if this angle here is 19.47 degrees, this one, these two have to add together to be 90 degrees. So theta 3 is going to be equal to 90 degrees minus theta 2. So that's going to be 90 minus 19.47 degrees. So that's going to be an angle of 70.47, not 47, 53 degrees. So now, theta 4 and theta 3 are going to be the same thing because this is reflecting, and we know that the angle of incidence and the angle of reflection have to be the same thing. So theta 3 equals theta 4 equals 70.53 degrees. Now when we go up to theta 5, well, our normal lines are again going to form a right triangle. So we're going to have theta 5 is equal to 90 degrees, and then we're going to have minus theta 4. So this is going to be 90 degrees minus 70.53 degrees. So we're going to be back to 19.47 degrees. So our last thing we need to do is apply Snell's law on this boundary, and then we'll have theta 6. And I'm going to go straight to our rearranged equation. So we're going to have theta 6 is equal to arc sine. In this case, we're going to have n5 over n6 sine theta 5. We're going from glass to air here, so it's going to be arc sine of 1.5 over 1 sine of 19.47 degrees. So this is going to work out to be 30 degrees. And if you think about it, that makes sense because we go from air to glass, and then we're coming out, we're going from glass to air, so it kind of makes sense that we're just reversing the process when we come out this side. So are there any questions on this example? Alright, so we're going to move into our last topic for the day, which is ray tracing. And so the idea behind ray tracing is, let's suppose that we have an object and we have a lens. If you take the lens and you put it by your object, the light from that object is going to come through your lens and it's going to create an image. So you can think about this like with your camera. If you want to take a picture of something, you aim your camera lens at it, you take the picture, and it creates an image. Now what's happening in your camera is a little bit more complicated than the general idea of an image because it has to process the image, but it's the same basic idea that you have an object, you have a lens, that light goes through the lens and it creates an image. So let's suppose we have our camera lens and we want to take a picture of Cupcake the kitten. So and let's say we want to figure out where that image would end up being. So there are a few key features to this. So the first thing we have is we have an object distance, and that's just how far is our object from the center of our lens. So this is the center of our lens here, and our object, Cupcake, is located here. So we're going to denote this with an O, and O is this length here. And it's called our object distance. So this here, this is our object distance. And I believe the book uses S and S prime for object and image distances, but Mr. Dudish prefers we use O and I because they're a little more intuitive, so that's what we'll be using. Now I also have what's called a focal length. So I'm going to make our focal point here. I'm going to denote it with an F. And the focal point you draw symmetrically on either side of the lens, so this is our other focal point F. And the focal length is just that distance that it takes for you to focus. So your eye acts as a converging lens, and if you take your hand and you hold it close to your face, there's going to get to be a certain point at which your hand's going to look blurry. So you bring it close enough, and your hand looks blurry, and you can kind of pull it back, and then you hit a point where it's focused. So the focal length is that distance from the center of the lens to that point where the image focus is. So F is your focal length. Now I also have what's called an image distance, and that's just going to be the distance from the center of your lens to your image. So we don't have it on the board yet because we haven't drawn it yet, but I is your image distance. So ray tracing is a method to figure out where your image is going to end up. And so to do this, there are three principal lines that we can draw. And so the first one we want to draw is going to go from, all of them start from the top of our object. So we're going to go from the top of Cupcake's head to our lens in all of these cases. So the first one goes in parallel to the axis, comes out through the focal point. So I'm going to denote that as parallel and focal point. So we start out parallel, we hit the lens, and then we go through the focal point. And I'm going to try and color code it. I think I flipped my colors in my last section, so I'm trying to do it right in this one so that the video will at least have the appropriate color coding. Because we're going to do another example in a moment when Cupcake is inside the focal length, and that's a little bit trickier. But the process is still the same. So we start by going parallel and then through the focal point. We could also go through the focal point and then parallel. So the purple line is going to be focal point and then parallel. So we're going to go on the top of Cupcake's head, through the focal point. We're going to hit the center of our lens. We're going to come out parallel. And really we should be doing this with rulers to get these lines nice. But we're doing the best we can with the board. And so the last line we're going to draw, we just go straight through the center of the lens. So the last one is through center. And it's just going to go straight down like this. And if we draw everything to scale properly, then we're going to end up having these three lines intersect. And the place where they intersect is going to be the location of our image. Now, so I don't have to draw a cupcake upside down, I'm just going to draw a little arrow to represent the location of Cupcake's image. And so this point I then, or this point here then, would be our image distance, and that's just going to be this distance from here to here. So our image distance is like this. And in this particular way, based on the way I drew it, it's pretty symmetric, but that's not always the case. So are there any questions about this so far? All right, well, what if instead of having what if instead of having Cupcake out here beyond our focal point, what if she was inside that blurry range? What would our situation look like then? That's where things start getting a little bit tricky. So let's try this. So we're going to start by drawing our axis in, and then we're going to draw our lens. We're going to draw our focal points. So this is one, and then this will be the second one, so that's our focal point. And we're going to put Cupcake right here. I'm just going to use a little arrow to denote her. And so we want to figure out, well, we're not going to get a true image in this case, we're going to get what's called a virtual image, and so we want to know the location of the virtual image. Well, this process works exactly the same, but it's a little more complicated because we have to trace back to figure out where our virtual image is going to be. It actually ends up back here. And so to make sure I have my color coding scheme correct, I'm going to look at this real quick. So our first line we have is parallel to the axis and then through the focal point. So we're going to go parallel to the axis and then through the focal point. Now what we're going to have to do is trace this line backward. And we're just going to use a little dashed line to do that. We're just going to trace it back because our virtual image is going to end up somewhere over here. So the next line we want to draw is the one that goes from the focal point and then comes out parallel. And this one, so we're going to start with a dashed line here. And then we're going to have a solid line here. We're going to come out parallel. And then we're going to draw a dashed line going backward. And then, and kind of the dashed lines are to represent, it's as though the light is coming from these places. It's not actually happening here, like everything that's past the object, like we're not actually getting the light from, but it's as though it's coming from these locations. So that's why we're using the dashed lines, is to denote that fact. Now our last line is the one that goes straight through the center. And once again, we're going to trace it backward. And we can see they kind of meet in this area. right here, not perfectly. And I'm going to use a little dashed arrow to denote that this is a virtual image. And so that's where Cupcake's virtual image would end up being in this situation. Now the thing about ray tracing is that if you draw everything to scale, you can actually just measure your paper and that will tell you the lengths you're missing. So let's say you're given your object distance and your focal point. If you draw that to scale and you can do your ray tracing process using rulers to make sure your lines are nice and straight. And where they all meet, that's going to be your image distance. So you can just measure that length and that would give you your image distance. It's really tricky to do, to draw these lines really nicely so they do all meet where they're supposed to. So on Wednesday, we're going to learn what's called the thin lens equation, and that's going to give us a way to mathematically determine our image distance or our object's distance or focal length if we are looking for those instead. So we don't have to do ray tracing anymore, or so we have another method so we can confirm our ray tracing by make sure that everything's ending up in the right spot. So are there any questions? All right, if there are no questions, then Wednesday we're going to do the thin lens equation, but if you have anything else you want to see, like anything we covered today that wasn't fleshed out as much as you would like, or anything we've covered like for review, so if there was something we covered a while back and you're not sure of, feel free to send me an email and I'll make sure to put that on the agenda for Wednesday. And otherwise, just have a great day.